present about CircleFRI, and so the main motivation is making the field more efficient. So there's like some trade-offs, and if you use smaller prime fields, then we can have fast arithmetic operations, but FFT needs large 2x subgroups to be efficient. And your Machine field form 2 to the power v minus 1 is efficient, but the problem is the two-adic subgroup, multiplicative subgroup. There's not big, not enough two-adic multiplicative subgroups. In like 32-bit architectures, we can have like very efficient arithmetic. For example, we can separate the high-low, and then this part is just modulo 2 in this pi. So how to make it FFT friendly? So we introduce a circle group, which is defined over the complex extension field, and this, and we need to have modulo 3 over 4 prime because this needs to be irreducible. Means that like this should not have any solutions. And the unit circle over this is defined as x squared plus y squared equals 1, and this is the same as the conjugate multiplication of the complex is equals to 1. And the conjugate is just x minus iy of the complex z. So the formula, so this, if we consider this unit circle group, then this actually has order multiplicative. This multiplicative group has order p plus 1. And the proof is not that elaborate, so I'll add it in the article. But yeah, we can just think of this circle group, unicircle group has order p plus 1. So which means we will have a good two-adic multiplicity in this group, because this is like 2 to the power of 31. And the group operation is defined as following. So this is just a complex multiplication. And I didn't really add it, but this is actually kind of represents the angular rotation. But if you think about the cosine sinus, but I'm not sure like how I can actually do like explain it with that trigonometric way in a finite field. But anyways, yep, this is the group operation. And 1, 0 as its neutral element. If you think like 1, 0 multiplied by 1, 0 is going to be actually 1, 0. And for any
then 1, 0 times any element computed 1, 0 group operation xy is xy.
Yes. And for any point in this circle group, we define tpxy, which is translation, but actually it can be also seen as rotation. So this is just simply pxx, just following the group operation, and it will result in actually a rotation in this circle group. Like, so the operation will be result in this one, right? So this angle is going to be same as this one. So this is the more intuitive explanation. And also there is a squaring map. So pi is actually a squaring map, and this will result in this if you do the group operation. And actually in this unit circle, the y squared is actually equals to x squared 1 minus x squared, so it will become this. And also the group inverse are given as x minus y, and if you do so this is actually just the reflection in the x axis. Now we define a twin coset. So twin coset is basically a union of two coset, but the two coset should be generated with q and inverse of q. So if you take a union of these two coset, then you get the twin coset D. And also this should be what is it? No intersection. It should be no intersection.
I have a question about slide 2 slides ago.
Which one? This one?
This one, yeah. So it says that p times x of y equals px times x minus py times y. And it says px times y plus py times x. Why is it flipped for the y?
Yeah, this is from the group operation, right?
Okay.
So the thing is, if you multiply, where is it? If you multiply this, like let's say this is like px, py, qx, qy, right?
Okay.
Then if you multiply, you get the real part is gonna be like
px
qx minus, because of the I squared, it's gonna be minus.
I see.
But the imaginary part is gonna be like just the plus, like
Okay.
x y I plus, yes. And so we're here, and so gn minus 1 represents a subgroup of power of 2 n minus 1. So if you take a union of these two coset, then it's going to be to the power of n size twin coset. So this blue is representing one coset, right? So let's say this is q g n minus 1 coset. So here the n seems to be like 3. So this is coset of size 4. And this is the red one is going to be like q minus 1 gn minus 1. So if you see this is, let's say, q, then blue is going to be the one coset, right? And the inverse of q minus 1 is going to be basically rotation in the opposite direction. So this rotation, and if we take a union of this, the whole thing is a twin coset of, let's say, 8 points, right? And we can see that twin coset maps to itself under inverse, because so we take inverse of this 2, then it just becomes q minus 1 union of q j minus 1. So it is, the union is of course commutative, so we can just, this is just same as itself, right? So what this means is inverse is basically reflection across the x-axis. So it just means that these twin cosets are all symmetric by x-axis, right?
Question.
Right?
Yeah. So for the circle group operations, I think it's like 2 slides before again. So like you said, oh, one more. The inverses are like the dot dot dot. The like one point would be the red, and then 1 point would be the blue, right?
Yeah.
First, is there any like diagram showing the squaring of the circle?
Squaring is basically, so let's say this blue, right?
Yeah.
So you can see that we can just rotate that same around, and it's going to be around here, right? So you can see that, you can say that the multiplication is actually rotation by the same degree.
Okay.
So if you multiply by itself, it's just 2 angle, 2 times the angle.
So it would be like the next slide, right?
What?
It'd be like the red of the next slide, like. So no, go to the next slide, and then like on the leftmost diagram, for example, if you had like take one of the red points, and then the next red point would be the squaring, like left would be the
This
squaring.
one?
Yeah.
I don't think so.
No?
No, actually, let's consider. I think it will be more. Okay, how to explain? So this is actually. Let's think about the blue square. Okay.
Okay.
So this is q times 1, and this is going to be q omega. Omega is the generator of G, let's say, right? So this is q identity, this is q omega, this is q omega square. So if you remove the q, it's going to be a subgroup, like points with here and here and here and here, right? So this is going to be identity, this is going to be omega, this is going to be omega square. So this omega square is here.
Yeah.
It's going to be here. So, right.
Okay, so then taking it back to the squaring map.
Okay.
So how does that translate to like our image then?
In which image? In here, this is just showing the inverse actually.
Okay.
There's no representation of the squaring map.
Okay.
Yep. So yeah, the twin coset is symmetric by x-axis, we proved, and then there is also a standard position coset. So it is a special twin coset. So this is also a twin coset, but it is a standard in the sense that this is also a coset. If you see, like, these are all evenly spaced, right? So you can see that this is, if you take Q as this, like this blue point, then Q times the subgroup of size 4 is going to be this, right?
Q times what?
Subgroup of size 4.
Size 4.
Yes. So group of size 4 is going to be this, this, and if you will rotate by this degree, 45 degree, then it's going to be this, right? So it's just a special case of twin coset that all elements are like evenly spaced, right? So this here is like a coset of subgroup size 8, subgroup of size of 4, and this is subgroup size 2, coset of size 2. And you can see that standard position coset of size 2 can be only this, for example, because twin coset, it should be like reflective in x-axis, right? And standard position coset should be like also evenly spaced. So this can be the only standard position coset of size 2.
Question then for the leftmost diagram.
Okay.
I don't understand how, like, I assume when it says evenly spaced, it means between like the 0, the omega, and the omega squared and omega cubed, right? But then for the first diagram, it's, if you look at one of the cosets, it's not evenly spaced between all of them.
Which?
Like, for example, if you look at the blue, and then you look at 0, omega, omega squared, and omega cubed.
Okay.
Like, it's not spaced evenly between those 4 points.
So you mean this? I mean, to me, they're all like 90 degrees spaced.
Oh yeah, but I mean, like the previous slide also has 90 degrees spaced.
This one?
Yeah.
But the problem is, for example, this 2 is not it's the same degree as this one, right? So this means that if you rotate a bit, right? Coset is basically rotated subgroup, right?
Okay.
So if you rotate it backwards a bit, this is not going to make a subgroup of 8 size because it's differently spaced. So in here, we can take omega as like element of degree 45, right? Then it's going to be like that subgroup rotated a little bit like this.
Okay.
Do you get it?
Yeah.
I hope I could draw it here.
I think I can kind of get it. But so pretty much the 2 case, there's only one possible case ever.
Yes.
And then also the second diagram, there's only that possible case.
Yeah, I think so. Yep.
And then, but for the first one onwards, there's like more than one possible case, since it can be like tilted slightly.
Also, it should be symmetric, right? Symmetric by x-axis,
Yeah.
right? So I think this one also is only one, defined as one.
Oh. Okay. Okay, I see.
So basically, so let's say it's like QGM, let's say, right? So coset of the group subgroup GM, right? This is QG like 8 maybe, like then the Q can be only generator by half, like kind of, to make it like symmetric.
Okay. It's just a very specific geometry
Yes,
case.
a
Okay.
very specific case. And if D is a twin coset of size 2n and n is more than 2, then its image, quadratic image, image after the quadratic mapping is a twin coset of size 2n minus 1. So it's like 2 to 1 mapping. In addition, if D is a standard position coset, so is the result of quadratic mapping. So the proof is like, let's get the quadratic mapping of D, then it's gonna be like this. So the quadratic mapping of the subgroup is gonna be a subgroup of size minus 1. I mean, divided by 2. This is actually 2 to the power of n minus 2. So, and then the PQ and PQ inverse. And this is also twin coset, right? And in the standard position coset, it's also gonna be same because the what is it? What's the group? Okay, I don't recall right now, but okay, I'll add it as well. So now we define the space of polynomials for the low degree testing. So this is bivariate space of bivariate polynomials defined like this. So over the unit circle, right? And then this is basically what low degree extensions are for univariate proofs. And they say the crucial properties of this polynomial space is that it's rotation invariance. I'm not sure. I mean, so this they say that this is crucial for this FRI to work, and also good superability. But I'm not sure like why they are actually crucial.
Does space of polynomials mean that you mean the diversion domain, or you mean the space that evaluation results are residing?
So in FRI we take polynomial. For example, in general FRI, the space of polynomial is just all polynomials of degree size n, right? But in here, it's all polynomials of all bivariate polynomials of degree. The degree of each element should be less than n.
Ah, I see.
Oh, so
Here, oh, sorry, you can go first.
okay, so the degree of each is n divided by 2, so that if they get multiplied together, it becomes n.
Yeah.
And here the degree means the degree of the multivariate polynomial, which means the maximum degree that can each variable in case x and y can have.
Yes.
Yes.
So one element will have like, yeah, maximum of degree n, you can say, like. And then we define a vanishing polynomial here as well, and so it is just a polynomial which evaluates to 0 over d. So if we decompose d into pairs of points, like any like pairs, like then we can take a product like this. So this is a bit different because it's univariate. I mean multivariate, bivariate. So x minus pkx. So you can actually put the points like pkx, qkx, y, and then you can see that this will actually evaluate to 0 in both pk and qk.
Oh, so I can understand that this is gonna be 0 over like pk because there's a x minus pkx and y minus pky.
Mhm.
What about the okay, say then so yeah, I understand that if the this gonna be 0 when the x and y is one of the pk something, but it's gonna be 0 more than that. Like there will be like pk comma let's say ok pk ok also be 0 pk yk also be 0, right?
pkyk? What is
I just the example like so this is not only pk qk pair but also pk with any other the second element going to be 0 when you evaluate at pk and any other point.
Yes, I mean I mean we don't. I mean we can divide into any kind of. I mean so d is even sized. Actually, where does it mention? Actually, d should be even sized so that we can divide into pairs, right? So we
So
can randomly actually divide into pairs.
so
So
the points here you talk about the points on the standard out points on the twin coset then that the points always reflective over x-axis.
The inverses?
I don't think so. I think we can take any random combination, random pairs.
Uh, then what do you mean even size n?
Otherwise, we can't really divide into pairs, right? Even size d.
No, open
Let D be a subset of even size N.
n.
Wait.
Yeah, top first line. D be a subset.
Yeah, so d is of
The
even
size
size.
of D is even.
Yeah, the size of d is even.
Okay.
Then this shows that there exists a vanishing polynomial. So let's say we evaluate at p, then it's gonna be this is 0 and this is 0, right? But at the q case, it's a bit different, but this is gonna be qkx. So this part is gonna be same as this one, right?
Mhm.
And this part is gonna be same as this one, right? So if you subtract them, this is gonna be also 0, right?
If qx qkx by pkx so that x and y can be either pk or qk.
Yeah. This can be
I see.
yeah. So we divide into n over 2 pairs, and we pick a product of like this, right? Then this is gonna evaluate to 0 and on any pk or qk, right? All points in D is gonna be evaluated to 0.
Okay.
So now we are given a twin coset D, and we can see that the square, if you keep square mapping like n minus 1 times, we will get a result twin size of 2, right? And then you can say that the the resulting points are this, because there's 2 points and it's going to be symmetric by x-axis, so it's just yd minus yd. And we can therefore like define this vanishing polynomial as this. So where Vn is actually this n minus 1 times quadratic mapping, and then taking the px projection. So the result of this is going to be either x dyd or x d minus yd, depending on the xy. And then if you take projection, x projection is going to be just xt, either case, right? So this is just xt minus xt, so it's going to be 0, right? And notice that
so only the vanishing polynomial that has only coset that has size 2 has a special form. Because if you look at the previous slide, this is not the same form with the next one.
Yes, yes. So yeah, this is not the same form. So we are just trying to, this is another form of defining, we can see that this vanished, right? So we can define this vdxy can be this also. But yeah, so this is for the twin coset case, right? But if d was not the twin coset, then it's gonna be different than this, right? So in the twin coset size, I mean twin coset case, we can define it like this. So
wouldn't all twin cosets result in like a y and then a minus y?
All twin cosets?
Yeah.
Yes, all twin cosets will result in this.
Then why do we go until pi to the n minus 2?
Oh, here there is many points, right? There is 2 to the power of 2 to the power of n points total in this whole union of 2 coset. But then if you take one quadratic mapping, it's going to be 2 to the power of n minus 1. And if you take it n minus 1 times, then the result is going to be just 2 points.
Okay, so like for example in the diagram I showed earlier with the 4 points,
yeah,
like the opposite corners could be the 2 points, which doesn't result in a proper like algorithm between the two.
Yeah, so for example in here, maybe after quadratic mapping, it's going to be this.
Yeah, but then we can't tell if it's like red, red, or like red, blue, or like we can't tell if it's the inverse.
Red, blue, I mean, the red, blue doesn't really matter because this is just a whole set, right?
All 4.
The twin coset is just all 4, so yeah, we don't really care about that.
Okay. So the reason why it goes to a twin coset of 2 is because that case is the only case where like xd, yg, and then xd minus yd will hold Fisher. Right?
The reason why we do this n minus 1 times, you mean?
Why you get n minus 1 times and then get a twin coset of size 2?
Because the starting is 2 to the power of n, and after each quadratic folding, we get 2 to 1 mapping, right? So the number of points is divided by 2, right? So we need to do n minus 1 times to get 2 points.
Yeah. So I'm just saying that if we didn't go to n minus 1, if we went to like n minus 2, it'd be 4 points, and then the 4 points wouldn't have like a set algorithm or set way to show them.
It will be a bit complicated to define, right?
Just a question from this slide. So you said that after n minus 1 squaring, it results in 2 sides. Then it means that if you don't square at all, that the total number of points would be like 2n.
Yes.
Then it means like, do we need one additional higher degree than expected polynomial? I mean like, so if the degree requires like, for example, in the Fibonacci example in the previous presentation, I only need 4 rows, but in that case, we need 8 rows for apply CircleFRI.
8
rows or 2 to the 3 degree.
Why do you say that?
Because n minus 1 squaring results in a size 2 twin coset. If you don't apply squaring at all, then if I calculate, it gives us like 2n twin coset of size.
Yes.
Then does it mean that if we want to prove for like degree 2 polynomial, do we need like degree A coset, which means do we need 2 times degree more than 2 times?
Actually, that is in fact true, but I'm not sure of the reason why. Like, I wasn't sure of the reason why they do that, and actually they have some additional stuff on it. So yeah, maybe we can discuss after the
Yeah.
presentation. So we can see that actually the v and xy doesn't depend on y, right? Because it's always xd, right? And when d is a standard position coset, then Pn minus 1d is again a standard position coset, and which means xd is 0, right? So as we've seen before, the only possible is this one, so the x is 0, right? So in this case, v dxy is actually v and xy, right? So the minus xd is 0, so and then vd can be evaluated by O(n) field operations, 2 addition and 1 multiplication in each step. So v on x is, for example, x projection of p0 xy, and p0 xy is just xy, and which is x, right? And v squared, v2x is just 2x squared minus 1, because like the x part of px, right? pxy.
Yeah.
So we saw, like, where is it? This part, right? So pxy is this, and we get the x projection, and we just repeat the same stuff, and then we can calculate vn over vn with O(n) field operations. Now we will define an FFT basis. Now we can define an FFT basis. So this J0 to Jn minus 1 is the bit representation of J. Then we can define order n basis like this. And then, so so what FFT will try to do is,
what is FFT basis? Is it like Lagrange basis?
Yeah, you can say it's like that. So we want to find these coefficients of these bases so that it evaluates to f over d, right? So let's define this circle FFT friendly prime first. So any prime which p plus 1 is divisible by 2n plus 1, then it's going to be called circle FFT friendly, and n is called the supported order, and 2n is supported domain size. So here also, like, yeah, there is p plus 1 is divisible by 2 power n plus 1, but 2n is supported domain size. Right? So there's some degree comparison. So, for example, the Mersenne prime of 31 is going to be, if you plus 1, it's going to be to the power of 31, and it's going to be 31 support order is going to be 31. So here we just, it is a theorem just that we can find these coefficients that evaluates to f over d, and we will get into the algorithm now.
Is it like inverse FFT then? Because something like, so
Yeah, I was actually confused. So in here, actually, you can see, not here, here. Where is it? So this is basically, this is indeed a circle FFT. So
yeah, okay.
they mixed it up. So consider the initial polynomial modulo so it's basically inside the space of polynomials. And here the y squared is modulo 1 minus x squared. So we can replace all y squares by 1 minus x squared. And hence all polynomials can be represented in this canonical form f0x plus y f x, right? So we will just separate all the elements with y here and non-y elements here, right? And then we can calculate f0x and 1x. We also like in general FFT we call it odd and even terms, right? And here we can find f0x at minus x like this. Since we're familiar, we'll just go over. So in the first step, this is like inverse mapping. Also, it's called X projection. So we can calculate f0x function like this, f1x function like this. This is the representation. So let's say we are given 8 evaluations, right? And this is so what this X projection is basically doing is the f0x is taking an average of this, right? So plussing this inverse, adding up this inverse map, and then dividing by 2. So this is just average of these two, right? So this is like 22 divided by 2 is going to be 11. So the red parts are the f0s representing. So this is going to be 7, this is going to be 5, this is going to be 4. And this is basically a difference, right? Difference divided by the y. And then it's going to be like plus 6, minus 6, minus 3, plus 3. So you can see that f0 is going to be like this, 1 is going to be like this. Any questions here?
Yeah. So in case of, so I'm talking about this. So this gonna be minus 10 over b. Oh. Ah, yeah, I got it. Ah, yeah. Yeah.
Divided by minus b, so it's
yeah,
same, right? So yeah, basically.
So the points that has reflection over x-axis are has the same value.
Yes, yes. So this is actually also 2-to-1 mapping. So we don't really have to put it like represent it in a circle. We can just define it in a line, x line. So it is wholly like dependent on just x. So the next step, also called quadratic mapping. So we get this 2, right? So k0 is either 0 or 1 from the previous step, and then we can define the quadratic mapping like this, because we can just like regular FFT, we can divide into odd and even terms, so that this evaluates to fk0x, and these odd and even terms can be calculated like this, just like before, and we just keep repeating this until we get constant functions of the form like k. This is like gonna be big representation, right? 0, 0, 0, 0, 1, 0, 1, 0, 0, something like that.
Could you help me how do you reduce the one from the previous slide to the here? Yeah. How did you reduce f0 to bivariate to univariate?
So it's already univariate here, right? As we see here, it's not really dependent on y.
Yeah.
So we can see that this is actually just univariate. So that's why we can just ignore the y here.
So where's k0 exactly? Is it just a random number? Or?
No. So k0. Let's say k0 is either 0 or 1.
Okay.
So let's say k0 is 0, right? So here we are folding this only. Okay. So f00 is folding of f0. F01 and F00 is folding off F0.
F0, say that again one more time. F0 and F1 is folding off of F0?
Yeah, so let's say let's say K0 is 0, right? Then this is going to be F0x, F0 minus x, which is this one.
Ah,
Okay.
Which is this one. And if K0 is 1, then if K0 is 1, then this is going to be F1x, F1 minus x, which is this one. So here we have two polynomials. In the next step, we will have four polynomials.
Okay, so is K, I still don't understand. Is
Or
K0
that-
random?
No. K0 is 0 or 1.
But
0
there's
and
two
1.
cases.
0 and 1. Both cases will be calculated.
Okay. So the first step, the first ever general case would be F0 and F1, and then the next case.
It's going to be F00, F01, F11, F10.
my question. Why it disappear abruptly? So here it has F1 as a Y. Right?
Yeah. So as we see here, this actually doesn't depend on y.
Y, yeah, I agree that Y variable doesn't depend. It's not dependent.
Yep.
But there's a scalar Y.
Yeah. There's a scalar y, but this is just evaluations, right? So we are reducing, like we're.
Oh yes, evaluation research. So when you just access the F1, it's just a number, scalar.
Yes.
F1 of x is just scalar.
So if you keep folding, if you keep repeating, we will have constant functions. I mean, constant evaluations of this, constants of this form, and then each of them is going to be the coefficients of the FFT basis. I'm not going with the proof.
Then my question is, the f of 2 times x squared minus 1 is definition, or is there any derivation?
This one?
Yeah.
This is the square mapping, right? Px.
Yeah.
I mean, just p.
Yeah.
I think it will be actually more. I also. Okay, what? So normally we put in the normal FFT we get x squared here, right?
Yeah.
X squared here, right?
Yeah.
So this is just x squared in the complex extension field.
Yeah. The unclear part from here is, I think there will be like derivation from the derivation, so that the logic from previous slide to this slide. But I think that is, I believe.
Logic. So we get that we will have these two, right?
Yeah. Could you
So
apply square logic here so that I can connect to the next slide?
square logic.
Yeah, because you try to apply, or is it just a definition?
Yes, you can say it's a definition.
I
So let's say we put, like, for example, what is it? Let's say we put a, right? Let's say x is a. Then 2a squared minus 1 is going to be f0a, fk minus a, right? So this is going to be just, let's say, 11 minus a is going to be 4, right? Minus minus a is going to be evaluated here.
Then I think
plus a is going to be evaluated here.
I think it would be nice to show us that.
So we actually have some calculations here. So f0x can be written like this, and f000, this is going to be this is going to be this, right, in the next folding. So f000 can be evaluated like this, 27 over 4. So how we get it is so f00 what is it? So oh okay I skipped this slide. So after one more folding, we get this 8. After one more folding, we will get this.
Wait, the 8 goes to 2? Wait, 8
This
goes
is
to 4 and then 2.
Yes. So as we've seen before, so this is just actually 4 points, right? I mean, this you can say this is just a 4 point. We don't really have to represent it on circle. It can be just x-axis.
Okay.
So it's going to be 4, 5, 7, 11, right? So just for just for like convenience of calculating the squares and stuff, in here they just put it as in the circle, right? So in here we will do the same folding here, and then it's gonna be like so 11 plus 4 over 2 is 15 over 2, right? This is gonna be actually a square. So the c is actually a square here, like a square minus 1 here, right? So the x-axis is a bit different, right? Because we have here f01 is gonna be 6 here because like what is it?
Isn't F01 the rightmost diagram?
Right. Yeah, we evaluate at yeah, the other evaluation is like the minus b case, right? So in here we have only 2 points, like a minus a and b minus b. These two possible values for the x here, and if we put it there, then we will get these 2 points.
I think what's good to have in the previous slide is, no, the next slide, just to show one example that how, so in the third line, if you replace k0 with like 1 or 0, I think it's enough to good to show us that the following the definition, if we replace all these with the definition, then we get the f0x in the previous slide. If you show us one example with this, then I think I can, accept.
So you're not sure this equation holds?
No. I mean, I can accept, but that should be exist beforehand, right? I mean.
You mean it should be like this or what?
Oh yeah, kind of. So what I mean by is that, so we know the f of 0 or f of 1x here, right?
Yeah.
So yeah, k0 is one of either 0 or 1, and if we follow so if let's say k0 is 0, then if we use this, and if we use this with times x, then it results in the same polynomial of in the previous slide, which is f0. Then I would like to accept the process, but
I think maybe
if you add this and this, this times x, right? So this is gonna be just fk0x, right?
I see.
This is just the same as the regular fry, so.
I see. I see.
So yeah.
I think definitely the next slides that show it in more depth kind of make it easier to understand.
Which one?
These, yeah.
Yeah, like this is. I agree that this is also confusing. I mean.
Wait, I don't. Okay, so those 2 points, if you get one of the points and then you add x times one of the points on f01, that equals like 11. Like for example, c, that 15 over 2 plus x times 7 over 2a equals 11. Is that what it is?
15 over, no, oh, you mean like.
How does f00 and f01 diagram?
Yeah, that's true.
Okay.
So this plus Uh, so this so so you're putting it in this equation, right?
Yeah.
So yeah, x is, let's say, a, right, in here. Then we said that this is actually c, right?
Yeah.
The c is actually a squared. So it's going to be 15 over 2 plus a times this. So it's going to be 22 over 2, which is 11, right?
Oh.
Mm.
Huh. Okay.
Hmm.
I guess the bottom one would be B.
So if you put b here, then it's going to be b like b, what is it, b squared, which is also like minus c. It will translate to minus c and plus b.
So does that mean for the opposite of F10 and F11, we have to input negative A and negative B?
Right.
It's like, oh, okay. So,
What?
like if we had F of 10 and then F of 11 instead?
Then these points are going to be different, right? Because this is going to be f1x. So
Oh,
it should come
shoot.
from this.
Okay, wait, then how? Okay, wait, next slide.
This is going to be f1x.
Okay, then how do you? Oh, you can't get that. You can't get negative B and negative A from F00 and F01 then, right? Can you?
Yeah, in here we can only have c and minus c. I'm not sure what.
Is it possible to create negative A and negative B?
I mean, even if we put negative a, let's say we put negative a here, right? Then this is going to be same because it's squared, right?
Yeah.
So this is just going to be same c. And this is going to be, this is going to evaluate the same because this is just a plus minus a. And even if we negate it, it's going to be same. So it's going to evaluate the same at 15 over 2. So yeah, you probably, it's going to be like maybe here minus this. Maybe there will be a point like here, symmetric. I mean,
Oh, that's confusing. Okay, I'll just think it's a given.
if you maybe try calculating it yourself, then
Yeah.
I'll try to make a clear example. But yeah, this is, yeah, okay.
Then does it mean that, so if you follow this diagram, then 2 times a squared minus 1 is c?
Yeah.
Okay.
And yeah, we will have these, and there's gonna be more, right? And now we can use the same FFT for FFT logic and the random linear combination, like of the even and odd to the fry. And this is a bit this can be a bit confusing. These S are just like L0 and like the evaluation domains of each step, you can say. So first, the evaluation is bivariate, and then the P1 is actually the inverse projection or J projection. This is going to convert our thing to univariate evaluation domain. And then we keep the square folding, and then we get to the final degree one, I mean the constant evaluation domain, right? And then
Question: shouldn't the final S be SR?
SR,
Yeah.
we have it. We have it. Oh right, this should be R. Actually, this is from the paper, so.
Huh?
Yeah. That's why I would have written like the L0, like traditional notation, right? The evaluation domain of step 0 is like written as L0, L1, etc. But in here they use like S0.
Okay, I'll just put a comment.
So I'll go over each, actually, like how it looks like. So we actually do do this decomposition step. So I'm not sure why this step is needed, but I'm guessing that this FFT can be only done in this domain. The so what they do is they they separate it into V. They take the Vn component outside, so we will actually evaluate over the Vn minus one. Like so, the prover will actually decompose into this form, and then the F0 is going to be inside this first evaluation domain, right? And then lambda is sent to the verifier so that so that they can verify this part. And then we start doing the folding here. So in the first step, the random beta is sent from the verifier to the prover, and prover commits to the function fi, which is just f1, l1, where in the honest case, f1 is going to be f0 0, beta 1, f1 f1 of 0. So even in the odd part of the first f0, randomly combined with the beta.
Where is the gamma used then?
Gamma? Lambda?
Sorry, lambda, yeah.
Lambda it's actually calculated by the verifier prover. It's not random.
Okay, so it sends it to the verifier, and then where does the
verification step?
Oh, it's not here. Okay, oops. Okay.
The query phase.
Yeah.
So this is J folding, right? So in the J folding, if you see this, so it's gonna be X, Y. This is gonna be X, Y here, right? So this is like square projection. I mean X projection, so it's gonna be F0 X here, like this. And this is inverse, so X minus Y, right? This is gonna be F I minus 1 X minus Y here, and this is just gonna be X, Y here. This is the same. This is just more what is it? More like kind of functional way to write this equation. So this is just Fj, right? This is just F, and this is just F0 pi xy, right?
The beta, so here the beta is replacement of, if you go to the page at 20, yeah. So beta will be replaced by X, right?
Yeah, replacement of X.
Yeah.
So yeah, just like a regular fry. So here, yeah, we do the J folding, and then here we do the square folding pipe, and then from the step 2 to R, we are gonna also get random beta, and then the Fi is gonna be constructed like this as well, but the function is a bit different. In here, not X projection, but not the X projection, but the square projection. And T is just minus X, so this Fx plus F minus X, right? And this is Fx minus F minus X.
Why is F minus X?
It's just another way of writing this one, F minus X. So this can be written as ftx.
Oh, but the T is the 2x squared minus 1?
No, T
Okay.
So this is just a more functional writing of
I see.
And in the final, after all the folding, we just send the final result in plain. And in the query phase, yeah, we take the initial x0 uniformly from the initial domain, and then first verify the J folding here. So we query F0 at x0 and the inverse. So in here, actually, this is the bivariate domain, right? So this is gonna be actually xy, right, inside x0. So jx is gonna be x minus y, right? So this is just also another way of writing the previous FFT case, and px is just x, right? Because this is x projection. Also same here. And then we query f1 at the x projection of x0, and this is actually the point of used in the next step, right? And then we check if this holds. Any questions here? So we calculated this one and this one here, so we just combine with the beta.
Yeah.
And in the square folding, we also the verified is square folding here for I from 2 to r, and here the next x is defined as the, oh, this should be square, right? This shouldn't be px. This should be square. This should be just pi. So this is going to be next xi is going to be the square of the previous one, and then we query I minus 1 at these 2 points, and then we can compute each of these. This should be I minus 1, sorry about that. No, you're, and then we do the same thing, we can just query at xi and check if this holds, because we calculated this 2 from here, and accept if all checks passed.
Okay, I have a question. I actually have two. One, do they use Merkle commitment?
Do they use Merkle commitment?
Yeah, because you said that commitment in commit phase.
Yeah, I think they will use the same Merkle commitment.
Then in the query phase, by the verifier should also verify the Merkle proof, right?
The query phase, I mean, yeah, so this query phase is actually like we need to verify, right? I mean, we can't just trust, right?
Yeah.
So actually, we are just assuming that this is
see.
all doing the Merkle check.
Okay. Where is? Oh. Okay. Is lambda only for the next line? Is it not mentioned in the query phase?
Oh right, I think. Oh no. Let's quickly check if this one. I think they just briefly mentioned that we should check it in the initial stage. Oh, this is this. So there's a preface. Let me see.
Is that every round or
the first 40 polynomial should be f minus lambda.
Oh, okay.
Because we started right folding from this polynomial, so we need to restore.
Yes.
And
Okay.
then another question. Can I?
Yeah.
So the question is, so it seems like maybe there will be handled in the next section or something like that, but so in normal case, when you open the polynomial, the domain is like field domain, right? But it just handles the case that the opening point resides in the
Merkle?
I don't know Merkle domain. Yeah, polynomial space, I think.
Which part? Do you mean this one?
I mean, yeah, maybe, yeah, x0, yeah. X0 should, yeah, in normal case or speaker case, like if you take a look in the CircleFRI in Plonky 3, we're gonna sample from the entire domain space. So they use a kind of deep technique.
Yeah, so here there's no deep, right? So there's no actually half domain sampling here.
Okay.
But they mentioned that if to actually make it useful in Stark, because just the proximity is not enough, they use actually deep domain extension to actually get. So and also go over the brief batch CircleFRI. This is just the same batching thing we do. So we get a random challenge or just random point, lambda b. This is just batching random, and then we just do the random linear combination of all the batch functions to make one f, right? And then we just run the protocol one, the previous protocol, on the resulting random linear combination f, and then yeah, but the query phase will also have to check this if this holds.
After, for in my view, so after some starting on a wall, I first thought like the F here is like the column in the table or circuit. After I reading a paper of wall again, then I realized that this f of i's are the unfolded polynomial and f is the folded polynomial. So in word paper they try to prove that even if folding happens, the distance is preserved.
So you mean, is there a proof of this, you mean?
Sorry?
Is there a proof that, I mean, so you're talking the correlated agreement stuff, right?
Yeah. I think this is very look like correlated.
Yes, actually the batch fry, the first batch fry was, I think, mentioned in the proximity gaps paper, which they go over the correlated agreement, and so which means just what the basic theorem is stating is if this is a code word, right, then is all of these a code word? So their main question is that. So we know that if all the FIs are code word, then F is definitely going to be code word, right? But from the verification perspective, we don't know if, let's say we only do the protocol one on F, and we know this is a code word. We verify this is a code word, but we don't know if these ones are code word. So do we actually can make a claim on that? And proximity gaps actually says that if this n is really smaller, like really small than the evaluation domain, like
Compared to the entire field size?
I think just yeah, compared to the entire field size. So the f over n squared over f, like quadratically smaller, I think. It's something like that. But yeah, I think I will have to, I separated the presentation, so I think I'll have to go over that correlated agreement and proximity gaps in the next presentation. And yeah. So yeah, they just use the same technique as the proximity gaps paper. And the result of this is, so actually this is just changing the, actually this is the optimizations just come from the field arithmetics because it's much cheaper now. So we can see here that this is actually one thread. So it's because they said there's a memory bottleneck in the big more threaded environment, but I think they said like this will be optimized in the future. And actually you can see consistent performance of 40% gain in the execution time in just a single thread in compared to BabyWare. So yeah, I'm not entirely sure. Actually, I think Ryan mentioned like there is we need to what is it? There is some degree difference,
Yeah.
right, in the FFT. I think that is the reason why they do this, why they do the decomposition step. But yeah, I'm not 100% sure, and I couldn't really figure it out. Maybe I'll look at it more. Apart from that, yeah, I think I can implement Circle Start now. CircleFRI now.
What?
I think I can implement CircleFRI now.
Oh, nice, nice.
Did you end recording?
Oh.